Alright, so welcome back. We are in Unit 4, Section B, Lesson 4. So we're going to be talking about stalls today. So we're going to watch this video real quick and talk about it. Alright, so I want to read those questions and just come up with something in your head about, why this was happening. So I think we all saw that the models were stalling. The nose-up attitude exceeded the wing's critical angle of attack, which caused the wing to produce less lift. So obviously without enough lift to support the weight, the nose dropped. And then once the nose drops, the plane accelerates and the angle of attack was reduced and resume flying. So as you guys are going to learn in this lesson, a stall is a loss of lift caused by an aircraft exceeding its critical angle of attack. So stated more plainly, a stall happens when the wing gets pointed too high relative to the oncoming wind. Sorry, I'm trying to scripted this out and I'm trying not to mess up what I have here. So be patient. Hopefully I get better at this. So stalls should be fairly predictable. You should know when they're coming. Pilots do have stall related accidents, and some of them are obviously deadly. So that's why you need to learn to recognize the conditions that are be leading to a stall and the warning signs so you don't ever end up in that situation. You guys will also learn how the recovery steps should the stall actually occur. So with the proper training, stalls are a normal and predictable part of an aircraft's flight regime. They can be easily avoided. Alright, so here's the slide on the critical angle of attack. So before, we talked about airfoils and lift, and there are two factors related to lift production that a pilot controls in every plane: the airspeed and angle of attack. In small angles, the increasing angle of attack results in more lift, and at some point the relationship breaks down and the lift drops off. Even when the angle of attack continues to increase. The point at where the lift drops off is always at the same angle of attack for a particular aircraft, because that angle is a fixed design feature in the airfoil itself. So the point at which direct relationship between the angle of attack and the lift breaks down is called the critical angle of attack. This is when the wings exceed the critical angle of attack. The aircraft is said to be stalled. So we can see that there. You hitting the stall point, your critical angle of attack, where the stall actually occurs. So again, like I said, a given aircraft always stalls at the same angle of attack regardless of the airspeed, pitch, attitude, or any other factor. Alright, so the separated flow. Alright, and showing these videos are too big of a pain, so what you'll need to do is open up the PowerPoint and click on them, or I will post the links for you. So at a low angle of attack, the airflow above and below the wing is smooth, so we can see a visual of that. And then as the angle of attack increases, flow near the top of the trailing edge becomes turbulent and eventually detaches from the wing at the separation point. Then as the angle of attack continues to increase, the separation point moves away from the trailing edge and towards the leading edge. So you can kind of see the development of getting to that critical angle of attack where a stall will occur. So There are different types of stalls. So for a given airplane in a given configuration, a stall will always occur, like at the same angle of attack. That's what we just talked about. It's a design feature. So a normal stall is a stall occurring at 1 G, and then accelerated stall is when you feel more than 1 G. Alright, so again, I will post the video so you can see the difference of those two types of stalls. So a load factor is the perceived weight experienced by the wing, the pilot, and passengers as a result of changing aircraft orientation. So a positive load factor is when you feel like you get pushed down in your seat, as though you weigh more than you do. A negative load factor is lifting you out of your seat. So an aircraft in a turn imposes additional load on the aircraft. At 60 degrees angle of bank, the aircraft and its occupants experience 2 times the force of gravity. G-forces can also be applied by sudden pull-ups, as when quickly going from a dive to a climb. And again, we got tons of videos this time, but it's hard to make a video within a video, and I might be violating copyright, so I don't know if I do that. So probably not a good idea. Alright, so the mitigating aerodynamic stalls. So predictable stall characteristics make the aircraft safer and easier to control. Aircraft designers take a lot of thought and put, their development into that. It happens in a way to keep aircraft controllable as long as possible, or delayed as long as possible, and happen in a way that give pilots warning. So among the tools and techniques used are wing washout, camber, vortex generators, and plan form selection. We'll be talking about those in just a minute. Apologize, email's blowing up, that's why you keep hearing that. So wing washout. It is designed for the wing root, the inboard portion of the wing there, we can see that, to stall before the wing tip. This allows the ailerons to remain effective even after part of the wing is stalled, and this gives the pilot the opportunity to recognize that the entire wing is about to stall. So to make sure that the wing tip stalls, last the wing is twisted so that the wing tip is at a lower angle of attack than the wing root. And yeah, yet again, another video to watch that you have to click back and forth between. Alright, so the wing camber, we've already talked about this, is engineered to affect stall characteristics. The greater the wing camber, the higher the stalling angle of attack. So increased camber can be used like washout to delay the stall at the wing tip, helping to maintain the effectiveness of the ailerons. The vortex generators. They're vanes that are attached to the leading edge of the wing. They delay the onset of the separation point by injecting a high-velocity airstream into the boundary layer. Vortex generators increase the critical angle of attack of a wing. And again, we'll watch the video. Alright, so can't really do this in small groups, but do it on your own, check it out, do some quick Googling, and just check them all out. Alright, so the warning signs, the visual cues be a high pitch attitude, angle of attack indicator, and low airspeed. Audio cues, stall warning horn, quieter airflow, and low speed stalls. So the kinesthetic cues. Alright, so the Buffett cues, I just googled that to make sure it was buffet. I don't know what the proper term that is, but that's just the vibrations you get when the wing starts separating. So that's just like a vibration you can feel. And then you got the stick shaker and the larger airplanes, and the stick pusher and the larger airplanes. And those are just a mechanism installed by airplane companies that actually shake the controls when you're going through those to let you know that something's not right on the bigger airplane, because you might not feel it as much on a smaller airplane. Alright, so stall recovery. But the first thing to think about is, the best way to ensure you don't have to deal with this is to follow the proper protocols and pay attention to what's going on so you don't end up in that situation. But you must be able to recognize that the aircraft is in a situation such as takeoff and departure that can lead to a stall, and recognize those cues so the stall doesn't fully develop. An aircraft in a stall condition isn't producing enough lift to stay airborne. It is not a hazardous condition as long as there is enough altitude to allow you to descend a little bit and then level out and straighten everything up. So you don't want any yawing or side-to-side motion to develop. So recognizing a stall early will minimize your chance of a spin and reduce altitude loss. Stall recovery requires reducing the angle of attack. Following are the typical steps a pilot will take to recover from a stall. Individual aircraft and situations may have additional steps. Left alone, most aircrafts will recover from a stall without pilot input, though perhaps with more altitude loss than desirable. So, you want to reduce your angle of attack, add power, use rudder to maintain your coordination, and raise flaps and landing gear. And again, I'll post the video. Alright, so spin. So a spin is a stall resulting from a combination of a stall and yawing movement. This is sometimes referred to as an uncoordinated stall. In a spin, one wing is producing more lift than the other. The wing producing less lift drops and the other rises, causing the aircraft to rotate. This rotation results in a corkscrew-like motion, and as the aircraft ascends on a nearly vertical flight path. So most general aviation aircraft will not enter a spin unless actively forced into one by aggressive pilot controls. So now we can talk about the 4 stages of a spin. So the first one there you see is entry. So the pilot intentionally or unintentionally provides the necessary elements for the spin, and including the stall and the yaw. So the incipient phase, you see there at the bottom, is the phase between the moment the plane starts rotating to when the spin fully develops. It says it takes about 2 to 4 turns for the airplane in this phase. The aerodynamic forces acting on the airplane in this stage are not yet stabilized. Airspeed is generally stabilized at a low and constant level. So your recovery phase, next one's developed. So developed phase is the airplane's angular rate of rotation, airspeed, and vertical speed have achieved balance, and the flight path of the airplane is nearly vertical. So basically heading straight down, spinning. So in small airplanes, for each 3-second turn, the airplane loses approximately 500 feet in altitude. It is expected that the airplane will continue in this state unless corrected by the pilot. And so the recovery phase is the corrective action you're taking to stop the spin. So depending on the airplane, this phase can last from 1/4 of a turn to several turns. So the most common actions for a pilot to recover from a spin are reducing the engine power to idle, neutralizing ailerons, and applying full opposite rudder against the rotation, and moving the controls forward to reduce the angle of attack. Once the rotation stops, the rudder is neutralized, the pitch is smoothly returned to a normal flight altitude, and power is added to maintain or regain altitude. So again, I will post these at the bottom in so you guys can watch them.